Let's talk muscle performance. How well a muscle does the functions that it does. In this case, I'm really going to focus in on how well muscle generates force. So how well the functions are carried out. In essence, the ability to generate force. What factors influence the ability of a muscle to generate force? These factors include things like angle of attachment, length tension relationship, and force velocity relationship, as well as fatigue. And I have that in italics because it's an interesting concept to talk about. Now, angle of attachment, I'm actually really talking about two things there. The angle that the muscle tendon interacts with the bone. But for the purpose of this presentation, I'm really going to focus on pennation angle, the angle of the muscle fiber within the muscles. Let's start there. So angle of attachment and pennation angle. And what I have here are some different cartoons of different illustrations of muscle fiber organizations. Each line here represents a muscle fiber. This here represents the tendon unit that would connect ultimately to the bone. So these muscle fibers are at an angle, okay? That angle is called pennation angle. This is a unipennate muscle. There's a bipennate, like a soleus. It's a multipennate, so like the pectoralis or radial type muscle is organized a little differently. So here, this is the pennation angle of a muscle. And it's important to understand how pennation angle does influence muscle force. Now, we focus that more in biomechanics and physiology because it has to do with the direction of the force vector generated by the muscle fiber. And that's what this model here represents. It's just a mechanical model of a muscle tendon unit where it has some contractile element, some series elastic element, and parallel elastic element. Not critical for this class, not critical for physiology of endurance performance, but good to be able to recognize that pennation angle influences the amount of force a muscle can generate. Next relationship that we should know is the length tension relationship of muscle contraction. What this relationship tells us is the amount of force a muscle can generate is a function, in part, of how long the muscle is. So this graph here just illustrates that point, the relative tension. Let's just use force here on the y-axis and percent resting length. So this is 100% resting length. This is if we took the muscle out of the body, threw it down on a table, and it would flop around and it would come to a resting length. That's what that 100 represents. It's interesting, it's actually hard to know what the resting length of a muscle is in vivo, in the body. In vitro, in a test tube, or testing the muscle out of the body, we can determine the resting length a little better. But in vivo, it's a little hard. Some estimates of that, but in essence, here's what we have. The longer the muscle, the less amount of force, this is lower force, the less force that can be generated. And if you pull the muscle so long that the thin and thick filaments are not interacting with each other, there's zero force generated by the contractile element of the sarcomere. That's going longer. Going shorter, the amount of force generated by muscle also goes down, ultimately going to zero if the muscle is shortened so much that the thin and thick filaments can't interact with each other in a way to cause contraction. So let's look at this, just a schematic of that. So this is This shorter region is in this region here. And we're getting some confusion in terms of the myosin head, or excuse me, the actin filaments running into each other, and there just are not enough binding sites allowed when the muscle gets too short. When the muscle gets too long and the thin filament is separated from the thick filament, that's where we would be here. We can't generate force. So an optimum length is where there's good overlap of the thick and thin filaments. This is easy to demonstrate, and if we were in class, I'd have you do this, so good to try it at home. So here's 2 fingers. Grab your fingers and squeeze as hard as you can and generate lots of force. All right, once you do that, relax, and then go through some wrist extension, and then try to contract again. And what you'll be able to notice right away is you cannot generate as much squeezing force when you go through wrist extension. Why is that? Well, some of the muscles that are related to finger flexion are getting stretched by going through wrist extension. And so you're going into a longer region and you have a less ability to generate force. Likewise, if I go through lots of wrist flexion, I can't generate as much squeezing about my fingers for the same reason. The amount of tension generated by muscle, in this case, muscles generating finger flexion, is reduced when the muscle gets too short. This is a problem with muscles that cross 2 joints, especially muscles like in running, the hamstring that crosses both the knee and the hip. And you do have to be careful in running because you often are asking the hamstrings, the posterior aspect of the thigh, to generate hip extension and knee flexion concurrently. Well, hip extension shortens the muscle. Knee flexion continues to shorten the muscle. And so the ability of the hamstrings to continue to flex the knee is hindered by hip extension because of the length tension relationship. Hip extension shortens the muscle, less ability to generate a shortening force, and less ability to generate knee flexion during the stance phase of gait. Okay, the other key factor that I want to talk about is force-velocity relationship. What this relationship tells us is the amount of force a muscle can generate is partly a function of how fast the muscle is trying to contract. All right, and this is a very classic graph of that relationship. On the y-axis is force. There's just different ways to represent it. It's just normalized so that 1 represents the maximum isometric force, okay? And then on the x-axis is velocity of shortening. And again, just units are normalized so that the maximum velocity that this muscle can shorten is a 1, and then everything else is relative to that. And if I extend the graph out on this side, this would be negative velocities, or velocities where the muscle is actually getting pulled longer. So this would be eccentric contraction on this side of the graph. On this side, this would be concentric contraction. And at 0 velocity, we would have isometric contraction. So this line right here is the one I want to zero in. I want to focus in on. This represents the amount of force generated by muscle. And this is in vitro data. This is testing the muscle outside the body. What this is telling us is that as the contraction of the muscle increases in velocity, that is, we're telling the muscle to shorten faster and faster and faster, the ability to generate force decreases, okay, in concentric contractions. And that has to do with how quick the myosin heads can change shape, pull the thin filament, release the thin filament, and then re-energize to a high energy state, bind again. That cyclical action will, the ability to generate force will just go down as we're trying to do that faster and faster and faster. You can think of it as a tug of war. You know, if you have one team just sort of release the rope and all the people on the other side start pulling the rope as fast as possible, any one hand, you probably have a lower amount of hands in contact with the rope at any time because you're trying to pull the rope so fast. Okay. On the other side, though, something interesting happens when we go through stretching the muscle while the muscle is trying to contract. We actually see this increase in force. There's lots of discussion as to why that is. On one hand, this goes back to our muscle function presentation. It may be that there's more force generated to break a myosin contraction, a myosin connection with the actin filament. That might be part of the reason, that part of the explanation for why eccentric force goes up. Now, in vivo, we try to take advantage of this in training, and we do negative reps or eccentric reps to try to generate more stress on the muscle to generate a greater training stimulus. Interestingly, that doesn't always happen, and sometimes in the human body, when we're testing it with the muscle attached to bones, we actually don't always see this rapid rise of force in the eccentric side. But that's the concept that we're trying to do. All right, fiber type, the amount of force generated by muscle is partly a function of the fiber type. I should mention power. When we start talking about power, we talk about this in a math sense. This is one way to describe how much force of muscle is generated by talking about power, which is really the product of force and velocity. And if I go back a slide, that's what's being generated here. This is a product of force and velocity. And power is an important term, and we're going to talk about this a lot during the semester. It's the rate of transformation of chemical energy to mechanical energy. It's how fast we're transforming glucose, fats to mechanical energy or force. Okay, the more power we have, the more transformation of energy we have. And something to keep in mind is that different fiber types have different ratings for fatigue resistance. We have slow twitch fibers that are more fatigue resistance, and fast twitch fibers that have less fatigue resistance. That means they're more susceptible to fatiguing or performing over shorter periods of time. This is talked about in your book, type of athlete and fiber distribution. This is just some classic data for talking about different types of athletes. What we're actually seeing, though, is the fiber typing can be much more broad spectrum for any sport. And a fallacy of this type of approach is that you can test the fiber type of an athlete in certain key muscles and then predict what sport they will do good in. It's not always the case, all right? But this is the concept with this type of data. So sprinters will have a lower percent of type 1 fibers, therefore a higher percentage of type 2 fibers. Endurance runners would typically have a higher percentage of type 1 fibers and a lower percentage of type 2 fibers. But that's a big generalization. It's not always the case. And we got to really be careful about which muscles we're testing, which part of a muscle we're testing, and so forth. What we are finding is endurance athletes are benefiting quite a bit from including strength training in their endurance training performance. That strength training is really stimulating and stressing the type 2 fibers. Different physiological and physical requirements of sprinters. Sprinters are larger, typically. These are generalizations. Distance runners tend to be small, and we'll talk about this as we go through the rest of the chapters. There's some advantages besides just mass in terms of having a smaller mass for a distance runner in terms of thermoregulation. Explosive power, or the ability to generate force over a short period of time, very high for a sprinter. So sprinting 100 meters. Explosive power, I don't know why I have high here. This should be lower than a sprinter. Aerobic capacity, not important to a sprinter. You can hold your breath. Important for a distance runner. Fatigue resistant, that's unimportant for a sprinter. Critical for a distance runner. Muscularity, that's not a great term, but you need a lot of muscle to generate a lot of explosive power. That's why our power athletes tend to be larger. But it can be a disadvantage for distance runner carrying all that extra mass. And that's why a lot of distance runners tend to be smaller, as you have less mass that you get to carry over a long period of time. Just different body types, mesomorphic versus ectomorphic, and mostly type 2 fibers for sprinter and mostly type 1 fibers for distance runners. All right, so training, the whole idea of training is one, to train the muscle to generate force, but also to minimize fatigue. So I have defined fatigue in a previous presentation, but we can just go to Tabor's medical dictionary and we can define fatigue as a general tiredness. Or we can be more specific and talk about a reduction of force generating capability of muscle. I just want to be careful here because fatigue is not just a physiological response. We can be fatigued at the end of the day, and that just may be a mental fatigue. And we may have a hard time training or generating force from the muscle simply because our brain is tired. There's psychological fatigue. Sometimes what we actually talk about with studying fatigue is that fatigue is a mental state or a prediction of how much further you can go. So it becomes much more of a perception of effort that influences fatigue. And if you perceive that you can't go that much further, your brain starts to tell the muscles to generate less force. Okay, so fatigue is a really interesting term, interesting parameter to study. It's a really hard parameter to understand the factors that influence fatigue. But nevertheless, that's what we're trying to do, is train to minimize fatigue. So we can take a physiological approach and train the muscle to be high in fatigue resistance, but we can't forget that human performance is a broad spectrum of issues, and we will need to train the mental aspect of preventing fatigue as well, or minimizing fatigue. Develop muscle fiber types by training different intensities. This is muscle recruitment based upon a physiological model. And we'll get more into these models as we go through the semester, but Noakes uses different models to represent or explain different concepts. So a physiological model is explaining muscle recruitment just simply based upon intensity of exercise. That is, if we do a long, slow distance, the physiological model will tell us that, well, we're probably recruiting type 1 fibers. And if we're doing a high intensity, a sprint, we're probably recruiting type 2 fibers. Okay, that's a physiological model. Integrated neuromuscular recruitment model starts to set up what Noakes is known for, and that's the central governor model. And what this model tells us is that muscles are recruited based upon information received by the CNS, sort of like what I'm talking about here with fatigue being a perception. And what may be happening is that the brain may be monitoring different aspects, different physiological states, different mechanical states even, maybe even different psychological states. And the brain detects something that tells the brain or tells the system that you got to start shutting things down. So, or recruit muscles in a particular way. So maybe the brain has a cardiostat, that the muscle recruitment is controlled based upon the oxygen supply to the heart or maybe the brain. If you're not getting good oxygen to the brain, man, you better start shutting things down. If you're not getting good oxygen flow to the heart, you also want to start to stop exercising. And we know that in cardiac, that if we start having problems with heart oxygenation, ischemic conditions, we want to tell people to stop exercising, start to reduce the demand, the need for oxygen, so we can make sure that we get oxygen to the heart. Or maybe the brain is monitoring the level of blood glucose or the level of glucose in the blood, and maybe there's a glycostat. And is that important to protect the brain, because the brain really relies heavily on glucose to function? Or maybe the brain is monitoring thermostat. Maybe it's monitoring core temperature. You don't want high core temperatures. You know that when you get sick and you get a fever, you feel really bad. That fever can have some really bad effects on proteins in the body. It can denaturize proteins, so it can do some damage. So maybe during exercise, if the brain starts to detect that core temperature is rising, maybe the brain starts to shut muscles down, and maybe that's a source of fatigue. So we got to be careful. These are all hypotheses, right? There's lots of neat experiments out there now trying to test these, but they are hypotheses. And the idea here is when talking about fatigue and muscle recruitment and this integrated neuromuscular recruitment model, or really also known as AKA the central governor model, uh, the brain may be trying to protect the body from harming itself. You don't want to get too warm. You don't want to get too low of an oxygen supply to the heart or the brain, and you don't want to get too low on blood glucose. So maybe you start shutting things down prior to that. Central fatigue versus peripheral fatigue. Central fatigue is neurotransmitters within the brain change the signal sent to the muscle. So maybe this is a central explanation for fatigue. Peripheral fatigue would be maybe something is happening at the muscle site that is reducing the ability to generate force. So maybe unavailability of calcium. Is muscle recruitment influenced by perception of how much more work can be done? And that's how I started this slide. So that's just another way to look at fatigue is this perception. And we'll talk about this during the semester. Only the fast die, only the fast and strong die young. Oh, terrible. Endurance athletes tend to outlive and sprinters. There may be health benefits for endurance exercise. Maybe this is related to fiber type. It's not clear. Fiber type influences chosen level of physical activity. That might be a sociological aspect. People with more type 2 muscle fibers may be more prone to developing hypertension, diabetes, and obesity. These can all be risk factors for cardiovascular disease. People with type 1 fibers have greater levels of blood HDL cholesterol, again, a risk factor for heart disease. So just a summary of muscle performance. Muscle performance, the ability to generate force, is a function of the length of the muscle. It's a function of how fast the muscle is being asked to contract. It's a function of pennation angle and angle of attachment. It's a function of fatigue, which is a complex concept to go through, and ultimately, muscle performance is related to training as well, how well we train it to contract. And I did not get into the neuromuscular aspect of muscle performance, but that is another key component with training, is learning how to contract different muscles at the right time. And so motor coordination or control. Okay, that's the end of chapter 1. All right, thanks everybody.